a double integral, and then the boundary of x could involve a single integral. That would be Green's theorem. Or maybe Stokes' theorem if you're in R3. That's physics version of Stokes' theorem. Or if x is a triple integral, then the boundary of x would involve a double integral. That would be the divergence theorem. So you should be aware of the fundamental theorem of line integrals. I call it Fatoli. When you have a conservative vector field, which means that it is the gradient vector field for a potential function, that means that the line integral through that vector field is path independent. It doesn't matter what route you take, it only matters about the end point and the beginning point. Sometimes people need a little bit of convincing, but if you think about the fact that if a vector field F is the gradient vector field, that means that the first component would be the partial of that potential function with respect to x, then with respect to y, and then with respect to z. If you were actually taking the line integral of that, right, along a curve, you want to use, you have gamma of t as your curve. Gamma prime is really what you're dotting this with when you're integrating along a path. So gamma prime is going to be, we'll call that dx dt, dy dt, dz dt. So when you dot them with each other, really what you're doing is a to b are your beginning point, that your parameter value that corresponds to mapping to your beginning point, your parameter value that maps to your terminal point. When you take these and dot them, what does this look like? Partial of f with respect to x times dx dt plus partial of f with respect to y times dy dt plus partial with respect to z times dz dt. What kind of derivative taking rule does that look like? You've seen it before, I promise. It's probably your least favorite rule. Yeah, the chain rule, right? This looks like taking the derivative with respect to t of f composed of gamma of t, right? Because you take the derivative of the outside function with respect to x, and then you would take the derivative of the inside function, right? That's what that looks like. So when you're integrating, I should say this is out here. When you're integrating something that is already the derivative with respect to t, what does integrating the derivative do? Yeah, it just gives you the original function. So what ends up happening is that you have f evaluated at gamma of b minus f evaluated at gamma of a, and that's why it doesn't matter what path you take. The actual path doesn't matter, it only matters what the endpoint and the beginning points are. So that's the fundamental theorem of line integrals. Green's theorem is in the plane. You usually have a boundary curve C and a region R. Green's theorem is sometimes written, because we also wrote down like what these look like in calculus, or I should say more applied calculus textbooks. Not poo-pooing at all. But it's the line integral around the oriented boundary is equal to, this is usually what it looks like, q sub x minus p sub y, where f, the vector field, is q, p, q. That's two-dimensional curl over the region. I should say dA, because it depends on whether you want to integrate with respect to x first or y first or whichever. So that's Green's. The physics version of Stokes has a surface with boundary curve. So this is S, this is C. And you have this orientation where the boundary orientation needs to match the surface orientation. And if you have like a more applied textbook, they frequently talk about how in 21 we talk about the left-footed man or woman, person, unicorn. And if you're given the orientation for the boundary curve, as you travel it, your left foot should be soundly on the surface. So you're going like this, and your head will be pointing in the direction of the normal vector. So that's sometimes how we talk about it. Stokes is going to tell you that, right, the line integral around the boundary is equal to the flux or surface integral of curl over the surface. That's the way the more applied version looks. And then, of course, divergence involves a solid,